So we are recording right now. Mike, you have the word.
Okay, so Steve is a professor at the philosophy department of Carnegie Mellon, right, University. He has done his PhD advised by Mac Lane and Tide. He works with the semantics of type theory mostly, and this is what he's going to talk about today. I would like to thank Steve very much for agreeing to make this presentation for us. I'd like to say that we had more than 230 registrations for this meeting. And okay, so I guess this will be very, very nice. Steve is one of the most recognized researchers on category theory. And well, thank you very much again. And you can begin the presentation.
Okay, thank you, Mike, for that introduction. It's a pleasure for me to be here. If you have any questions during the talk, please feel free to just interrupt me, and then I will pause and give an explanation or correct technical problems with the video link or something like that. But I just warn you, I can't see the chat or anything like that here, so you can't rely on that to reach me. Okay, thanks. I'm glad to give the presentation. I understand this is a preparatory summer school for the category theory meeting in the spring, which I unfortunately will not be able to attend, but I'm glad to be able to participate in the summer school. As Mike said, I've been working on type theory, and both simple type theory and higher order logic and dependent type theory, Martin-Löf type theory for many years. And my main area of interest is the category theoretical semantics for such exotic systems of type theory. And in particular, most recently, maybe in the last 15 years, I've been focusing on categorical semantics for Martin-Löf's intentional dependent type theory, which is a constructive foundation for mathematics on the one hand, and on the other hand, a programming language for computer programs and formalization systems for mathematical theorems and proof checkers. And so it's experienced kind of a rebirth in the last 10 years or so, because people have gotten interested in this particular system of type theory for the purposes of computer proof checking. And systems such as AGDA, Coq, ROC, and now Lean are based on this type theory. And the type theory has a curious character, which I mentioned as intentionality. That was a kind of old-fashioned philosophical explanation of this curious character. And some years ago, we realized that that strange feature of the identity in this type theory, the intentionality of the identity, is captured by homotopy theory. And that was a big surprise and a unexpected development. This system of type theory that is used now for computer programming and was invented for maybe principled reasons in constructive mathematics suddenly is connected to homotopy theory, modern mathematics of continuous deformation and spaces and things like that. So there's a surprising connection between logic and foundations and constructive mathematics, computability theory, and homotopy theory. And so that's what we've been exploring for the past, 10 or 15 years. We call the system homotopy type theory. Basically, it's just Martin-Löf type theory, but with some additional semantical insights coming from the interpretation into abstract homotopy theory. So that's all by way of background. I'm not going to tell you much more about those details of that, but I just wanted to give you a little bit of background for what's going on. So the type theory itself is a very computational, constructive, foundational system. The homotopical semantics of the type theory import some kind of, what shall I say, maybe laxness or looseness or lack of strictness, because in homotopy theory, things happen up to continuous deformations. And that has been a little bit of a tension in this subject from the start. And so this current work that I'm going to be telling you about is about a way of resolving that tension by strictifying the homotopical semantics to match the precise strictness of the type theory. And so that's the topic for today's talk, is how to present strict algebraic, let's say, models of type theory into a homotopical setting. So I'm not going to review the homotopical semantics of type theory, as I said, but I am going to describe a strictification or a strict algebraic version of those semantics, which applies to homotopical settings and can be used to give semantics for the type theory. So that's the background. It's a lot of stuff, in the background there. If you're not familiar with all of those details, you can just take it as a black box. I hope that will be at least enough to allow you to follow the rough structure of the talk. And then if you're interested more in the homotopical background, I can give you some references for that. Okay, so let's get started. A homotopical model of type theory can be defined to be a Quillen model category, a Quillen with certain properties. A Quillen model category is a setup for interpreting homotopy theory. It's not a category theorist's thing. It's not a type theorist or logical thing. It's something that the homotopy theorists invented, namely Daniel Quillen, who got a Fields Medal for this description of the homotopy category of homotopy of topological spaces, homotopy types of spaces, and then other more general settings in which you can do homotopy theory. So if I have such a Quillen model category, and then it has certain conditions, some of which I'll tell you about, and what's called a univalent universe, which is something coming from the type theory, I can combine those ingredients and give the homotopical semantics for type theory, which I was just mentioning. So that's the basic background. Now, from such a model, from such a homotopical model, we can extract a strict model, and that's what I'm going to be doing today. And the ideas that I'm applying here are coming, on the one hand, from Voevodsky, who was instrumental in developing some of this interpretation, and also my students, Peter Lumsdain and Michael Warren, who were also involved in the early development of homotopy type theory. And we combine those ideas with some other ones that we're importing or borrowing from topos theory. And you might recognize that if you know some topos theory. We then put all those things together and we shake them up. And what comes out is a structure that is in fact equivalent to what's called a category with families. And a category with families, which was invented by Peter de Beer, is a very strict notion of a model of dependent type theory. So it's so strict and so close to dependent type theory that a type theorist will be happy with that as a description of semantics for type theory. Whereas a type theorist is not usually happy with the interpretations that category theorists like, such as locally Cartesian closed categories, which are not strict enough for the type theorists' strict rules of type theory. But a category with families is a good model, very strict, very precise, very accurate, a model of dependent type theory. So that's what we're going to end up with. And I'm going to explain now the general construction of such a thing. And then I will explain furthermore how to interpret the type formers for the unit type, which is easy, the sum type, the sigma of the type theory, and the product type of the type theory. I won't have time to cover the identity types, which of course are very important, and the universe, which is where the univalence lives. So those are additional topics that just don't fit. And then at the end, I'll step back a little bit and take a higher perspective, and I'll recognize that what I did is really what the category theorist will call a polynomial monad. And that's something that Mayk may have already mentioned, or at least the polynomial part, I think. And it turns out that this is a very familiar or simple concept, polynomial monad, which captures in quite a precise way the type theory. So that's the plan. So what's this type theory I'm talking about? You maybe have seen the lambda calculus and the simple theory of types, which goes back to Frege and Russell and Church and Gödel and all those people. Higher order logic with higher function types and types of pairs of elements of types and so on. This type theory is an extension of that simple type theory, but it adds a new feature, namely type dependency, where types can depend on a parameter. So let's explain that. We have the basic objects of the type theory are types. Here I'm writing them in capital letters. And then each type can have terms. I'm writing that here with lowercase letters and a colon to mean X is a term of type A, or B is a term of type B. And among the terms, there can be variables, and that's what I'm using letters from the end of the alphabet for the variables, following our old traditions. So you can think of maybe as a starting point, if you've never seen type theory before, think of the types as some kind of sets or collections or something along those lines. And then the terms are the elements or the members of those sets or collections or classes. Okay, but the terms can include also variables, which are, like a meta mathematical perspective. Now, the expression here with the turnstile is not, if you've seen it from logic before, it's not provability. Here it's just marking two different areas in an expression. The area on the left is where the variables get assigned their types. So it's a list of variables. Here I've only got a list of length 1. Here's a longer list, which includes variables and their type declarations. So X here is a variable of type A. And then on the right of the turnstile, we say, okay, given that X is a term of type A, this new thing that maybe I've constructed involving X and some other stuff, B of X, is a term now of type B, big capital B. And this capital B now is a type, but it has a parameter in it of type A, right? So we think of this as a family of types, B of X, varying over the type A. So that's the idea of a dependent family of types. And then we have a dependent family of terms of those types. And that's kind of the basic expression for this dependent type theory. We have these contexts. Now, if I have such a type family, I can introduce a new variable, y, of that type, and I can go on like that. And I get a context, which is a list of types together with variables of those types. And I'm going to write the context with capital Greek letters like this, just to have a convention to allow me to not have to keep saying context and keep writing out these long expressions. So the contexts are going to be lists of types, possibly dependent, and variables of those types. A substitution is a map between such contexts, which arises by substituting terms for variables, just like you always do in type theory and in mathematics. When you have a variable, you can assign it a value. And such a list of values of the variables will give rise to a substitution between the contexts. And then the distinctive feature of the dependent type theory really is these type-forming operations which act on dependent types and take here, for example, the sum of all the types varying over A. So we think of this as maybe pairs of elements, one from A and one from B, depending on that first one. And then the product of all the types in the family, just like the usual product of a family of sets, for example. And this is like the usual disjoint sum of a family of sets indexed over an indexing set. So those are the type-forming operations, and I'll be saying more about those. And then there are equations between terms. That's kind of the judgmental structure of the type theory, that two terms of some common type, so now I'm abusing this colon here. I'm saying this is an equation between two terms, each of which have type A. And the terms themselves may contain variables which are declared in this context, gamma. So given a context gamma with some variable declarations and a couple of terms, S and T, and a type possibly varying over these variables, I can say that these two terms are equal. And that's the basic expression of the type theory, is equality between terms of the same type in a given context. So that's the basic expression there that we're modeling. Here are some rules of construction for the type theory. So the type theory, like I said, is a formal system of foundations. It has rules, where you build proof trees, like in logic. You have some premises, which are axioms, and then you derive further expressions from the premises using the rules of inference. And in the case of type theory, because it's kind of a complicated structure, the rules specify a kind of mutually recursive system involving judgments, terms, types, contexts, and so on. So here's just a few of the rules, just to give you an idea of how things work. If I have a type and a variable and a type family varying over that, I can make a new context by extending this by one step, by introducing a new variable of this type. And now I've put it on the left of the turnstile here to indicate that it's a context. So the general form is this. Here's a context, here's a type in context, here's a new context, which I extend by one step by bringing in a new variable. That operation is called context extension, and it's important in the type theory. It's going to come up in the semantics. It's one of the things that I have to model when I give you semantics for this system, and I'm going to show you how to do that. Then there are the type constructors that I already mentioned. If I have a type here and a family of types in that context, there's a new type, sigma, which is, I think of as the disjoint sum of this family of types. I write it like that. There could be some other contexts back here, which I'm kind of dropping out of consideration because the action is here. But if there was a longer gamma here, then I need a gamma and a turnstile here. I'm not going to keep writing that again and again. Here's a term of type A. Here's a term of type B of A in a dependent type. I pair them up and I get a term of this type sigma. So that's how I introduce new terms of type sigma. A term of type sigma AB is a pair of a term of type A and a term of type B, possibly with dependency on the first argument. If I have such a term C of type sigma AB, well, then it has two projections. It has a first projection, which gives me a term of type A, and a second projection, which gives me a term of type B. But now B, remember, was dependent on A, and so I have to give that a value, and the value is just the first projection. So the second projection as type B of the first projection. Okay, I hope that makes a little bit of sense. And now these operations, the pairing and the first and second, have some kind of obvious equations that go with them. If I take the first projection of a pair, I get the first term. If I take the second projection of a pair, I get the second term. And if I pair up two projections, I get the thing I started with. So these are the equations for the sum type, the sigma type. And that's how the rules look for all the type formers. They consist of a formation rule, and some introduction rules, some elimination rules, they're called, and some computation rules. So the type theory is kind of set up in this schematic way. Here's another example, the product types that I told you about. If I have a dependent family of types over a type, I can make the product of the family. So that's the introduction or the formation rule for the product types. If I have a term of this family of types, possibly depending on the parameters, then I can get a term of the product of all the types. And the distinctive notation here is lambda x of type B. And this goes all the way back to Gottlob Frege, this notation, or at least the idea. And that is, this is now a function. Lambda xb is a function which takes arguments of type A and returns a value of type B, where the B might be varying in that same argument. So it's a dependent function. We think of it as a element of the Cartesian product or the big product of all those families of sets. So that's the notation for function abstraction using the lambda. And then if I have such a term, maybe I got it through a lambda or some other construction, it's a term of this function space or this dependent function type, and I have a potential argument of type A, I can apply the function to the argument and I get a value. So that's what this is saying. Oh, that highlighting is convenient. Okay. And then this value has type B, but of course, since B is parameterized, it has to get a value for the argument, and the B will just be the A here that I stipulated here as the argument. So the function evaluates with the argument to give me a value of type B of A. That should look a little bit familiar here. And now, of course, there are some equations. And the equations are simply this. If I abstract a function and then I give it an argument, well, then I get the thing that I abstracted from to start with. And if I take a function and I evaluate it at a variable, and then I abstract at the variable, then I get the function back out. So those are the two computation laws for the product types. So, and then there's a general operation here of substitution of terms for variables that I mentioned before. If I have a substitution, I mean, you can think of this as like a function from this collection of types to this collection of types, all organized nicely into a sequence. And then I have, what's going on here? Gamma A, oops, sorry, this is a little bit awkward. I guess the idea is this, oh yeah, here it is. The A is a dependent type over gamma. There we are. And then this is a term of that dependent type. Then I can re-index this family, which is indexed over gamma. I can re-index it by sigma to get a new family that's indexed over delta. And what I do is I just plug in the sigma everywhere in the variables that occur in this context. I plug in all the values of the sigmas, and I get a new family of types and terms that are now indexed over the delta. So this operation of substitution of terms for variables gives rise to a re-indexing of these indexed families of types and terms. So that's that operation. Okay, those are the basic rules of type theory. And the way that the category theorist models these things is maybe what Mike already mentioned when he explained locally Cartesian closed categories. You think of the dependent types. Let me go back here. There we go. You think of the dependent types as a family indexed by this thing. So that would be maybe an object in the slice category over this object. A family is an arrow with a codomain A, and a domain being the sum of all the B's. And then you use the sigma and pi from the locally Cartesian closed category to model these operations. So that's a little bit telegraphic there, that description. But here we see maybe the idea that Y is a family of things parametrized by X. So that's the LCC, locally Cartesian closed idea. And then the substitution is by pullback. I hope that Mike explained how, locally Cartesian closed category, if you have such a family like this, you can pull it back along any map along the bottom here. And now the basic structure that we're going to use to model the type theory is called a natural model of type theory. It works in the category of presheaves on the base category, and it uses this basic new idea, which is the idea of being a representable presheaf. So, of course, you know what a representable presheaf is, I hope, from the theory of presheaf categories, but this is a representable map of presheaves. And here's what it means. It's a natural transformation between presheaves on the category C. I'm assuming this is a category theory meeting, right? Everybody knows what a presheaf is on a category and what it means to be a representable presheaf on the category. This Y is the Oneida embedding. If I have a natural transformation between presheaves on C, I'm going to say that natural transformation as a map is representable, not if it's in the image of the Oneida embedding, but if every map from a representable in the image of the Oneida embedding pulls back to another representable so this will be in the image of Oneida here. So another way of saying it is, if you think of this as a family indexed over the codomain, all the fibers of the family, all the pullbacks over the representables are themselves representable. So that's the notion of a representable natural transformation. A natural transformation F of presheaves, Y to X, is called representable if whenever you map into X from a representable object, the pullback along that map of F is again a representable object. That's the definition of a representable map of presheaves. And now what I'm going to try to explain to you is we can use this to give semantics for dependent type theory. In fact, we can give very strict semantics, namely category with families in the sense of Dupierre. If you've seen category with families before, I hope you'll recognize it when I start to unpack this definition. I'm going to unpack the definition of a representable natural transformation into something that looks like a category with families. So the objects and arrows of the category, index category C, over which I'm making the presheaves, I'm going to think of as a category of contexts and substitutions. So the objects of C, I'm just going to write here with capital Greek letters and think of them as contexts, like context of the type theory. And then the arrows of C are going to be the substitutions from the dependent type theory. So that's how the interpretation is going to work. If I was doing this formally, I would give a recursive specification of how to interpret contexts using the inductive specification of the rules of construction for contexts to determine maps in C as the substitutions between the contexts. But informally, we just think of the objects as contexts and the arrows of C as substitutions. The definition of a category with families is given by a presheaf on the category of contexts, and the values are in the category of sets. So here we have our category of presheafs on C, and a particular such presheaf is the types in context. So we have a presheaf of types, and then we have a presheaf of typed terms which incorporates the dependency of the terms on the types. So this is a kind of maybe familiar construction where you take a category of presheaves and you slice it over a presheaf, and that is equivalent as a category to the presheaves on the category of elements of that presheaf. So I'm using that equivalence right there. If you're a category theorist, I hope this is a song that you recognize the melody of. It's a slice of the category of presheaves over a presheaf is also a presheaf category over the category of elements of the thing you're slicing over. And I'm making use of that in order to unpack this thing as a second presheaf and a map between the presheaves. So this is what I'm going to use to define the semantics in terms of representable natural transformations, and it's an unpacking of the notion of a category with families. So suppose I have a representable natural transformation like this in the category of presheaves. These are the types, these are the terms. This map P is the typing of a term. It takes a term to its type. This is the presheaf of types in context. This is the presheaf of terms in context. The P gives the typing of the terms. And the interpretation now, a little bit more formally, is this. If gamma is a context and A is a type in context gamma, that's what this expression means, remember? Then I'm going to interpret A as an element of the presheaf of types over the context gamma. This is a presheaf, so it has a value at gamma. So this is a set, and A is an element of that set. And similarly, little a is an element of the presheaf of terms over gamma. And then there's a map from Ty to Tim, that's P. And that tells me that little a has type big A. So that's what I'm saying here. If I apply P to little a, I get big A. So here's a diagram that represents this information in a very concise way. The correspondence that I've written here as double wiggles is nothing but the Oneida lemma. So because, after all, an element of the presheaf Ty at gamma is a natural transformation from Y of gamma, the representable, into the presheaf. This is the Oneida lemma. It says maps of this form correspond to elements of this form. And so I'm using that to interpret these expressions. So an expression gamma and then A is a type in context gamma is modeled this way. So I think of Ty in the category of presheaves as the object of all types, and then in a context, which is a representable, I have a map from the context into the object of types. So the parametrization of this dependent type on the context gamma is now captured by this idea of a function or a natural transformation or a map from this object of variables into this object of types. Right? A is a type, and so it's a thing in here, but it's parametrized by these variables. So this idea of A being a dependent family of types over gamma is now reformulated in this hopefully more familiar way for a category theorist as a variable element of this object parameterized by this object. So that's the kind of key idea there that we're making use of. It's maybe a new idea. We parameterize objects of the types by variables using presheaves in this way. And the same for terms. A term is an element of the presheaf of terms at this representable, and that corresponds to this, and it corresponds to a map from the representable up to here. And then I just compose with the typing to say A has type, little a has type big A. It's just saying that this diagram commutes. Okay, hereafter I'm going to drop the Y for representables, and I use the Greek letters to remind me that I'm talking about representable functors. Okay, so one thing I have to model, now I'm going to start going through the rules of type theory and showing how this models them. One of the rules was this substitution business, right? If I have a substitution of contexts, which I think of as a tuple of terms with some variables that I can substitute, and if I have a type in context gamma, I can substitute into the type, that's what the square brackets means, and get a new type in context delta. That was one of my rules. If I have a term of that type, I can substitute into the term, little sigma for substitution, right? Greek for contexts. I can put in the little sigma into the term and the type and get a new family of terms in the new family of types indexed over delta. How do I interpret that? Well, in the type theory, I just perform the substitutions. I put in the terms for the variables. In the semantics, here's how we interpret it. If little a is a term of type big A in context gamma, well, I said that's what this triangle means. Here's sigma. I substitute the sigma for the variables in A by composition. That's the most elegant, beautiful way of describing substitution. I put in the function values of sigma into the variables in gamma. I plug that into the function A, and I get a new function A with sigma substituted in, and I just compose those two things. And now this has the right shape, right? It's a element of the object of types parameterized by this new context delta. So that's a family of types in context delta. Same for the terms, right? Here was a term of parameterized by gamma. I substituted in the sigma, and now I get a new term parameterized by gamma, by delta. And now I have to check that the typing works out. If I had little a of type big A, after I perform the substitution, I need little a of type big A in the substituted thing to work out. And of course it does, because if this triangle commutes and I precompose the whole triangle by sigma, I get a new outer triangle that commutes. So that's the key idea there, that commutativity of a diagram is preserved by precomposition into the diagram, and that gives me a new commuting triangle. So even if you don't know anything about type theory or natural transformations or representability, you can see that if A commutes with the typing with the big A, and I precompose with sigma, then the precomposed little a commutes with the typing with the precomposed big A. That's the idea that we're going to be really exploiting here. It's a new idea in the semantics of type theory, that we make use of composition to give us a substitution. Okay, and furthermore, if I continue like this and do another substitution, well, it turns out that a substitution and then another substitution is just a single substitution for the composite of the two things. Similarly for terms, there's an identity substitution, which acts trivially on the types and on the terms. And this is the basic laws for a category of families, which I said is a strict model of type theory. So if you've seen a category of families before, this might now look familiar. If you haven't, this is at least an illuminating, I hope, way of modeling parameterized types and terms, just using this structure of presheaves. Remember, there was this operation of context extension that I called your attention to before. If I have a type in context gamma, I can make a new context by adding a variable. Well, I need to model that operation, and that's where the representability of the natural transformation comes in. I need to have, here's the key idea right here in this diagram. This is a representable natural transformation. If I have a type in context gamma and I make a pullback, I get a new context here. And that's the extended context, which I write gamma dot A, which is the new extended context over gamma. And it comes equipped with two projections, the first one down to gamma and the second one over to the terms. So that's the representability of this natural transformation is exactly what's needed to interpret the law of context extension in the type theory. And here's a little proof. You can look at the slide. I'm not going to go through it. You can look at the slides later if you're curious about how this works. That says this being a pullback square is exactly saying that this substitution gives the right, behaves in the right way to be the context extension. There are laws in the type theory which are modeled precisely by this square being a pullback. So that's the basic setup there. And it gives us the laws for a category of families. If you look at the paper of Peter de Beer, you'll see these equations. And they're modeled exactly by this condition of this thing being a representable natural transformation. Okay, now, so that's my notion of a natural model. I kind of explained it to you. It's a representable natural transformation over the category of context. It turns out that this is an essentially algebraic notion. Just because category theory is algebraic and pullbacks are algebraic over the theory of categories, and we use the Oneida lemma, and we can show that such a thing can be captured in a generalized algebraic way. It's a dependently typed algebraic theory or a finite limit theory in the sense of category theory. And the homomorphisms between these things correspond to exactly syntactic translations of type theories. Because it's algebraic, there's an initial algebra. There are free algebras that you can build over types and terms. And this really corresponds to the intuition from type theory that the type theory, and you apply the rules, is generating freely some sort of inductively defined structure. That's the idea, maybe, that the type theorists have developed, that the type theory is a way of presenting an inductively defined structure. And that corresponds exactly to what I'm telling you here, that these models are algebraic in a generalized sense. And the ones that the type theory gives rise to are the free algebras. So the deductive rules of type theory can be regarded as a procedure for generating the free algebras of this kind. So how do I model the type formers? I've spent quite a bit of time explaining the basic setup to you, so I'm going to move a little more quickly through this, but that's good because Mayk has already done this work for me by explaining to you what a polynomial endofunctor is, and I'm going to make use of that now to model the type formers. So suppose I have such a model of type theory. I'm going to write it like this. P goes from U dot to U. I think of U as a kind of universe of all the types. I think of U dot as a universe of all the terms, because a term is like an element of a type. So the dot is like a pointed object. So, and then this is the typing of the terms. It gives a term and it returns its type. And now I'm going to take such a thing in the category of presheaves and construct from it a polynomial functor. Here's the category of presheaves. Whenever you have a map in a locally Cartesian closed category like this, it determines a polynomial endofunctor, which I think Mayk explained already. So I'm just going to write big P for this little p for the polynomial endofunctor determined by little p. And here's how it's defined. If I take up presheaf X, that's a thing living in here, and I apply the polynomial endofunctor big P to it, it returns the value, which I hope you've seen before, this expression. That's why it's a polynomial. It looks like a polynomial. And these A's indexed by U are the fibers of this map. So that's what this is saying. The bracket A is P inverse of this map at A in U. So that's the expression for the polynomial functor big P determined by the map little p, and that's what I'm going to be using to interpret these type formers. Here's a construction of polynomials. I think Mike hopefully gave you this already. If I have a pre-sheaf and here's my P, the way I construct this polynomial functor is first I make the product like this and the projection, then I push it forward using the right adjoint of pullback along P, and then I get something here, and then I forget the indexing, and that is the value of the polynomial big P applied to the argument X is the domain of this map. So schematically here and literally here, the functor from here to here is a composite of 3 operations. The first operation is this pullback to the slice category. The second operation is push forward along this map P, that's a pi. And the third operation is forget the indexing. I'm already using the sigma and the pi notation here in anticipation of the interpretation. This is the locally Cartesian closed structure of the category of presheaves. And I'm going to be using that to interpret the type theory. Such a polynomial has a universal property, which I'll make use of. If I have some context or representable functor and I map it into the value of the polynomial at X, maps like that correspond to pairs of maps, one into the base, and then I pull back, and from there, one into the argument X. So this is the universal property of P of X. A map from gamma to P of X corresponds to a pair, big A, big B, of this form, big A into U, big B from the pullback into the argument here, X. Maybe Mike already talked about that, I don't know. I'm going to use it though right now. So if I apply P, now I give it an argument, not X, but rather U itself. So I'm doing something kind of funny here. I'm applying the polynomial determined by this map to this object. And then I unpack the universal property. Then what I see is a map into P of U corresponds to a pair by the universal property, the first term of which is a type in context gamma, and the second term of which is a type in an extended context, namely gamma extended by A. And now I'm using the representability here of this natural transformation to interpret the context extension of gamma by A, right? A is a family of types in context gamma. Here's the context extension. Here's the universal property of the polynomial. I get a pair A, B, where B is a type in context A. So this is really kind of the key idea of this interpretation using polynomials, is the universal property of the polynomial interprets the context extension and the types in an extended context using maps into a polynomial like this. A map from any context into the polynomial, a map from any context into U is a type in context U. A map from a context into the polynomial applied to U is a type in the extended context, extended by the first factor. So, and now I'm going to make use of that interpretation. I think I'm kind of running a little bit behind time, but that's okay. We're going to dwell on this because this is the really kind of key insight here for these semantics. I can interpret the type former for the pi types, which I had a rule for. Remember, it was this rule that I showed you. I think I'll go back and look at that rule. here was the rule for the pi types. It has a formation, an introduction, an elimination, and a computation. All of the rules of type theory have this schematic form: formation, introduction, elimination, and computation. For the pi type in particular, these rules, these 1, 2, 3, 4, 5 rules, cash out now using the polynomial setup to exactly the commutativity of this square. Well, more than that, the fact that this is a pullback. So those 4 rules are interpreted now using this machinery of a representable natural transformation and its associated polynomial endofunctor by saying that this square, which is the polynomial functor applied to this map, gives a pair of maps like this, and that interprets the 5 rules of the pi types by saying that this square exists and is a pullback. So let's just do it a little bit slowly, and then I think I'll kind of be done, because this is really the key idea here to explain the semantics. This is, remember, the type now of types in an extended context. That's the polynomial applied to you. And so the formation rule says, if I give you a type in an extended context, I can apply the pi and get a type. I think I have there it is. This is what the expression P of U means. It's a type in extended context. It looks like this. A is a type in U. B is a type family indexed by A. So an object of this type is a pair like this. It's a type in context of another type. And then I take this thing, I apply pi to it, and I get a type. No longer in an extended context, just a type. And that was exactly the formation rule for the pi types. Remember? The formation rule said, given a type in context of another type, you apply the pi and you get a type. So this map is the interpretation of that formation rule, which says this above the line and this below the line. And this exactly the same thing is working up here for the terms. If I have a term in an extended context here, a term of type B in context A, I apply the lambda, I get a new term. That's the object of terms. And what type does it have? Well, apply the typing natural transformation. It has this type. So this is saying, if I start over here, this is a term in the context extended of A. If I start here and I go around the square, then the square commutes. That tells me that the effect of lambda on such a term is a new term of this type. So the commutativity of this square is capturing the introduction rule for the pi types. The lower map is the introduction is the formation for the types. The upper map is the formation for the terms, the introduction, and the commutativity of the square is the typing of the introduced term. And then I'm not going to go through the details of it, but the elimination rule is given by saying, if I start with something here of that type, then I get something back here. This is exactly saying that this square is a pullback. So to say that the square is a pullback square captures the formation, introduction, elimination, and computation laws of type theory. So once you see that, and I don't expect you to see it immediately now, given all the stuff I've introduced, but just take my word for it. If nothing else, take it as a black box. We've captured the rules of type theory in a very concise and practically useful way by saying we take this map, it's representable, we make the polynomial functor, we apply the polynomial functor to the map itself, and then we make a pullback square here. And that captures structural rules for the type theory and the type forming operations for the product type, the pi type. And exactly the same thing works for the sigma type. I'm not going to go through the details, but there's a similar construction here involving the composition of the polynomial functor with itself, and then a map representing that polynomial, and a pullback square, which again captures the formation, introduction, and the pullback captures the elimination and computation rules. So the modeling for the sigma type is also given by a pullback square, just like the pi type. And here's the theorem. Maybe of course I can't explain it to you, but now you have a little bit of a high level idea of what it means. So if you want to read one of the papers that's in the references at the end of this talk where this theorem is proven, hopefully you'll have a little bit of orientation there. It says, if I start with a Quillen model category, that was again a homotopical model of type theory that's a little bit lax. If I start with a Quillen model category, from that I can construct, and here's the construction, a natural model, that's one of these representable natural transformations, in the category of presheaves over the original category of the Quillen model structure. The category of presheaves on the category of types hosts a natural model, a representable natural transformation built in this way. And that natural model will interpret the sigma and pi type formers in the ways that I just showed you, namely with those pullback squares, provided that the Quillen model category that I started with is right proper, which is something that the type theorists, something that the homotopy theorists have determined. It's part of the theory of Quillen model categories. So there's a known classical notion of a right proper Quillen model category. For example, maybe the canonical example is the category of simplicial sets equipped with the Kahn-Quillen model structure, where the fibrations are the Kahn fibrations. That's a Quillen model structure. It is right proper, which is a technical condition from homotopy theory. This theorem tells you that there's a model of type theory with sigma and pi in the Quillen model category of Kahn simplicial sets, which models sigma and pi types in the way that I've described to you. It models them strictly in the kind of strictest possible notion of a category with families in the sense of de Beer. So the theorem is a strictification of a homotopical model given by a Quillen model structure into a very algebraic model of a natural model, representable natural transformation, modeling sigma and pi types in that polynomial style that I just explained. So that's the theorem. It's in the paper, at the references at the end. And now I want to, in the 0 minutes that remain, I want to take a somewhat higher perspective on what's going on, which I hope will make sense to you, given what Mike did in the tutorial. If I have such a thing, I can model the rules for the terminal type very simply by saying this is the terminal object, this is its unique map, also admits a pullback square here. And now the pullback squares for this thing that I just showed you, and this one, which was the sigma type, they determine Cartesian natural transformations between the corresponding polynomial endofunctors. There's a polynomial endofunctor determined by this map, which is the composite of this polynomial with itself. And this Cartesian square is a natural transformation. The polynomial endofunctor here is the identity endofunctor. And this is a Cartesian square is a natural transformation from the identity into P. So this structure now is, I hope, familiar, this is the structure for a monad. It's a natural transformation from the identity endofunctor to this endofunctor P, and a natural transformation from P squared to P. And this is arising from the sigma types. This is arising from the unit types. And it's the underlying structure of a polynomial monad. So if I have a natural model, it models the unit types and the sigma types, then it has the structure of a Cartesian monad. Here, just briefly, are the monad laws. You might be wondering, if you're a category theorist, you know that a monad has some equations. These are the usual monad laws. They translate, they unpack into the type theory, where this sigma is the sigma type and this tau is the unit type, to these laws which hold in type theory, right? If I take a sum of units, I get the indexing object. If I take a sum over a unit, I get the object in the family. The sum operation is associative. Those are exactly the monad laws. What about the pi type, you're wondering? Well, the pi type is exactly an algebra for the monad. Of course, what else could it be? If you have a monad, you want to know what the algebras are. The pi type is an algebra. So, and here are the laws for an algebra for the monad, and here they are expressed in type theory. So from a higher perspective, the rules that I've shown you are nothing but the rules for a polynomial monad and an algebra for the polynomial monad. I pack all that stuff up because it's a very neat notion into a single concept. I call it a Martin-Löf algebra. It's a locally Cartesian closed category equipped with a map and pullback squares involving the polynomial of that map, which give a monad structure and an algebra for the monad structure. Whenever you have a Martin-Löf algebra in a locally Cartesian closed category, it models type theory in the way that I showed you. In a very strict sense, it models the sigma, pi, and unit type formers for the type theory. So that's the summary of the talk. I know it's, so here are the references. I know it's a lot of material to digest in just 1 hour, but I hope it gives you a high-level survey of what is going on here. And then if you want to learn more about it, you can look at these references. Here's the one that is kind of, the talk is based on. Here's the basic setup of natural models and the correspondence between natural models and de Beer's category of families. Here's the polynomial monad business together with my student Clive Newstead. Here's a more traditional approach to semantics of dependent type theory using category with families. Here's the name Peter de Beer that I mentioned. And here's the thesis of Clive Newstead, which gives in complete detail everything that I've talked about today in Clive's PhD thesis. Okay, that's it. Thank you very much. Let's see if I can get back to our shared screen. Yeah, there we are.
Yeah.
Oh no. How do I get rid of the infinite mirror, which is it's kind of cool, but it's also disturbing, I think.
Yeah, it should have a way where you can share only a part of your screen. But
Maybe
for now, you can stop.
How about that? How about that?
Yeah, that's fine.
Okay.
But anyway, first of all, thank you so much, Steve. Great talk.
Oh, you're welcome. Yeah, you're welcome. Thank you for your attention. Yeah.
Well, we already have a question here, but maybe someone that is here and would like to just talk. So
Sure.
maybe Hugo could start.
Hi, Hugo.
Hi, Steve. Thank you very much. Was a
you're
very
welcome.
beautiful talk, and the subject is amazing. I'm very surprised. I
Thank you. Thank you for saying so. Yeah.
Know anything about this, and
Yeah.
I'm very impressed. How it's what's the consequences of this framework? What you are doing with this now?
Thank you for the question. Yeah, I agree. It's very surprising. There's this kind of remarkable, amazing, unexpected connection between the type theory and these categorical structures on the one hand, the homotopy theory, and now the new kind of breakthrough has been this strictification using categorical algebra and the theory of polynomial functors. And then you can apply the theory that we know and love from categorical algebra of monads and algebras for monads and that sort of thing. So it's kind of wide open to apply some machinery that we know from categorical algebra to produce or to explore this connection with type theory. So just for example, we could try to, and we have been successful in making precise the type theorist's intuition that the system of type theory is some sort of a inductively generated structure. It has this big mutual recursion, which generates inductively some sort of a inductive or recursively defined data type or something like that. We can make that precise by saying, yeah, it's a free algebra for this polynomial monad. And we can use the machinery, going back to Max Kelly with the free monad on an endofunctor. We can use the machinery of categorical algebra to capture exactly that idea, to show that the type theory is a free polynomial endofunctor equipped with an algebra for that polynomial endofunctor, which is the free algebra for the polynomial. And that's quite a precise and rigorous concept, which is not just the feeling that the type theorist has that they're generating some sort of an inductively defined data type. It's a precise description of this thing as a free algebra for a freely generated polynomial monad. And one of the things that you can then do, having shown that, is you can prove something about the free algebras. And one of the things that you can prove, for example, is that if you do this in a setting that admits some homotopy theory, like a Quillen model category, the whole theory works there. It has the homotopical character. You can show that the free algebra that you build in that way is what the homotopy theorists would call zero truncated. That means it's not a higher type with some non-trivial homotopy theory and coherence issues, or maybe some unresolved equations. It's actually a set. So you do it in the homotopical setting, you have some higher homotopies, but the free algebra is still a zero truncated object. It's a set. And that tells you something about the algebraic character of type theory, that when you freely generate this structure, it remains tractable. It remains actually decidable. The equality relation is tractable on the freely generated algebra. And you can prove that formally now using this machinery. And there's a recent paper, which I should have included in the references, maybe I'll add it later, just from a few months ago, which shows that the freely generated thing is in fact set truncated. So that's just one example, though. You can do a lot of things with this setup now. You can add higher inductive types and import the homotopy theory of spheres and higher homotopical structures and so on. Or you can prove a normalization theorem for type theory, which the type theorists and computer implementation people are very interested in, which says that the type theory itself has a property of canonicity and normalization. It provides a kind of decidability that's important for type checking in a computer implementation. And you can use the algebraic character of the type theory that we've analyzed out now to prove things like that about the type theory. So there are lots of potential applications that are very exciting, back into type theory from this algebraic and homotopical analysis. I'm sure there are applications going in the homotopical direction too, but maybe we'll just leave it at that.
Thank you very much, Stephen. Amazing. If I made my very quick comment, that it seems that algebraic set theory is just a initial step to this much more flexible and powerful tool. It's this
That's right.
more or less the same idea, but and the free algebras are the main stuff. But the powerful of this new approach of type theory is amazing, much stronger than algebraic set theory. This Martin-Löf algebras.
Yep, thanks. That's my point of view as well. The idea of algebraic set theory was a good starting point, and then once we apply it to type theory, it works there too, and then it becomes a much more powerful tool. I agree. Thanks, Hugo. I think Mike has a question. Who's going to moderate?
Yeah, Mike can go.
Okay, so I was thinking those models, they are always somehow classical, right? I mean, they have some sort of, because you're building them upon set, so, and locally Cartesian closed categories, so it has some sort of flavor of classical logic, doesn't it?
Well, no, you can do this in any LCC. You can build the Martin-Löf algebra. It makes sense in any locally Cartesian closed. It actually makes sense in a more general notion than LCC even. So it doesn't have to be, there's no classical logic there. I mean, it's a very constructive.
Okay.
It's completely constructive. The example of Prisheev's of sets is, of course, it uses the category of sets, but it works in a much more general setting.
But I mean, I was thinking about the distributivity law that holds. And so the distributivity law is some sort of type theoretical axiom of choice. That's what I was thinking about, actually.
Well, yeah, that's a type theoretic version of the axiom of choice, but don't confuse it with the axiom of choice for sets. It's a different principle. It's a distributivity of sums over products, but it doesn't imply the classical axiom of choice for sets, which would be a very classical principle. So that's a feature of the type theory, that it has a constructive version of the axiom of choice, which is not the same as the one for sets.
So we have other questions here right now, besides the one that is read on the chat. So I will read this question here. So the person had to leave earlier, but since this will be recording, I think we can answer this now. So he's asking, does this theory have relation with the univalent foundations?
Oh yeah, absolutely. Yeah, this is the same. The homotopy type theory is another version of another word for univalent foundations, or univalent foundations is another word for homotopy type theory. And this kind of model extends. So the one I mentioned at the end, the example that I gave you at the end in the Kahn-Quillen model structure on simplicial sets, that's the basic model of univalent foundations. So the answer is yes, it's the same subject, yeah.
More questions?
I have another one. Can I?
Yes, of course.
So you were saying that the pi structure is an algebra for a polynomial. Actually, the polynomial, the lift of the polynomial to the arrow category.
Yep, that's right, yeah.
Okay, but It's a little bit obscure to me, but can you say something more about the relation between those two um, um, constructions, the monad itself and the algebra for the lifting? How are they related? I mean, because it seems that you are deriving one from another, right?
Yeah.
But from the in the lift, and I would like to know how does that work? I mean,
Yeah. So the idea is that, I mean, the monad on the arrow category, of course, is equally well described as two monads and a natural transformation between them,
okay.
right? And the reason we have to do that lifting to the arrow category is simply that we're operating kind of automatically then on families of objects rather than single objects. By operating on arrows, we operate on a whole family of objects that we think of as the arrow. And then we have the monad on the arrow category operates on the families in a uniform way. And
Okay.
it
Yeah.
simplifies the description then
Yeah.
by saying we have a lift of the monad to the arrow category. It's acting on the families in a uniform way.
Yeah.
Does that
Makes sense.
make sense?
Yeah,
Good.
makes-
Good.
yes, yes, yes.
But that idea is quite a fruitful one, and it's coming from topos theory, where in topos theory you have a sub-object classifier, and it's a kind of it's a generic sub-object, and then operations on that will translate into operations on all the sub-objects in a uniform way.
So this is some sort of the same idea as the internal algebra structure, Heiting algebra structure of
Yep,
the subobject classifier,
exactly.
which is some sort of monad as well. Yeah.
I said on the first slide we used some ideas from topos theory, and that's what I was talking about, is that in topos theory, any operations that you have on predicates or propositions like conjunction, implication, quantification, and so on, they can all be translated into operations on the sub-object classifier. And then those operations are automatically parametric in the types that are mapping into the sub-object classifier. And the same idea is being used here by putting these algebraic operations on the universe, the U, and then those are automatically parametric in the families of types which are classified by the universe. That's the idea.
Okay.
Okay.
Do we have more questions? Comments? Well, I have a question for myself.
Okay.
So I was just thinking, so this talk and the paper is a part 1. So What are you thinking for the part 2? What are the next steps?
Oh, thank you. Okay. So one thing is to do the identity types and the universe, which I left out of this part, right? And then, so that would be part 2, is to add the identity types and the universe. And then you've got a model of full homotopy type theory, univalent foundations in this same polynomial style. And then part 3, if I get ambitious enough, is to use the setup to investigate the category of such things. Because of course, once you have made a thing, if you're a category theorist, you want to know what are the maps between them. You want to make the category of all of them and then study that. And so that's the real goal, is now I have the things. They're Martin-Löf algebras. I can make the category of Martin-Löf algebras. I can make the free Martin-Löf algebras. I can make products of Martin-Löf algebras and constructions on them and presheaves of them and all the comonads of them and all the constructions that we know and love from category theory, we can now try out in this new setting. That's the idea.
Great. Yeah, thank you. So, more comments? Yeah, please.
No, I was just going to say maybe that's a good place to end with.
Yeah, definitely.
I'm sorry I can't come for the conference in the spring. I was invited to the conference and I have to decline. I'm going to be committed. I'm going to be on sabbatical in Cambridge in England, and it wouldn't be fair to. There's an expression, you can't dance at two weddings or something like that. So
Yeah. We understand. Yeah. But we thank you for being here, and we understand the situation.
Okay. Yeah. I look forward to interacting with you more in the future in some other way.
Oh, great. Yeah. We are gonna make new opportunities for this to happen.
Great. Okay.
So
okay.
Let's thank you, Steve, again.
Thanks. Yeah. Thanks very much for your attention.
It was great. I just finished the recording here.
Okay. I will send my slides to Mayk, and then he can pass them on, and please feel free to post the slides on the web as well.
Great. Perfect. Thank you.
Okay.